Okay, as we know, we have started the famous, celebrated Fourier transform in continuous time. And the first example that we have seen for the Fourier transform was this example, e to the minus at u of t for positive a. That would correspond to a decaying exponential. Now, of course, a decaying exponential is necessary for the evaluation of the Fourier transform, because if it's a divergent signal, then the integral for the evaluation of the Fourier transform, which is given at the top, x of j omega, capital X of j omega, will not converge. For the existence of the Fourier transform, therefore, we need to have the Dirichlet conditions that we already had for the Fourier series. So the same conditions hold here. The number of discontinuities, the number of oscillations, the number of zero crossings should be finite, and the signal should be convergent, integrable in other words, at least. So this was our first example. So that example starts at 0, jumps to 1, and then decays. So in general, it shows, or it exhibits, a low-pass characteristics, and the Fourier transform was 1 over a plus j omega. And the low-pass characteristics comes from the magnitude of the Fourier transform. You have to first develop the absolute value, or the magnitude of x of j omega, which for this case is equal to 1 over square root of a square plus omega square. So omega is in the denominator, and as omega increases, the denominator increases and the magnitude decreases. So it has this kind of a shape. Okay, and this shape indicates that most of the energy, or the larger energies, are around 0 frequency, which is nearer to DC. And as frequency increases, this thing decreases. So that's why we are referring it to be sort of low pass. And then we also have, for a complex entity, we have the magnitude and the angle. The angle term is indicated with an I of x of j omega, the angle of x of j omega, that is, which is equal to, for the numerator complex exponentials, it is arctangent of, or tangent inverse of, imaginary part divided by the real part. Omega over a. Why is omega over a? Because, as you see, the imaginary part is omega and the real part is a. So omega over a, arctangent of that, will give you the angle. But since it is in the denominator, it comes with a negative, a minus of arctangent. So that is the angle. So you should somehow check the methods of how to find the magnitude and the angle of complex variables. And if you want to just combine a complex entity, let's say, I don't know, gamma, to be equal to the magnitude of gamma e to the j angle of gamma, sort of expression is valid. Okay, that's how you decompose. And the low pass, high pass, etc. characteristics comes from the magnitude of omega, gamma. Sorry, it's not omega. Sorry, the magnitude of gamma comes from that. The angle, for the time being, is not very important for our purposes. So that was our first example. Let's see another time signal, and let's try to find its Fourier transform. And that time signal is quite a simple one, an impulse. Okay, what is the frequency counterpart of this thing? What's the Fourier transform of an impulse? Impulse, when we discover the Fourier transform, we will see that it contains a lot of high frequency. Because from 0 to infinity it jumps, and it comes back from infinity to 0 within a very short distance. So it is very high frequency, but it also has low frequencies and even the DC. And if we just write down the integral formula, which is from minus infinity to infinity x of t e to the minus j omega t dt. We just need to substitute delta t e to the minus j omega t dt here, from minus infinity to infinity. And here we come to a point to make a decision. Now delta t is arbitrarily short, very narrow, okay, and it only exists at t is equal to 0, nowhere else. For even very small t is equal to epsilon values, it is all zeros. So this is non-zero only at t is equal to 0. And from here we conclude that whatever we multiply it with, which is e to the minus j omega t term, that term, the value of that term to be evaluated is only at t is equal to 0. All the others will be multiplied by 0. So what is e to the j omega t at t is equal to 0? Yeah. At t is equal to 0, this becomes 1. Which means we need to find the integral of delta t times 1 dt, which is the area under the impulse. And what's that? 1. So the Fourier transform is 1. It's not even a function of omega. Independent from omega, regardless of what frequency we have, it is always 1. Just we can plot it then. X of j omega is all, sorry, this is t, is all 1s. It's an all-pass system, isn't it? It's a low-pass, a high-pass, a mid-range. Everywhere it exhibits something. I'm sure you must have watched some films regarding to that, or you may have heard about that. Do you know the concept of a white noise? Have you ever heard of anything called white noise? There is even a film regarding that, a Hollywood blockbuster. White noise. White noise is a noise which is almost impossible to predict. That's a very arbitrary noise. And there's one reason for the name. Why is it white? And what kind of a signal does it correspond to in time domain? A white noise is a noise whose spectrum, that is Fourier transform, in other words, is constant for all frequencies. Which is this, which happens to be this. And do you know why they call it white? Why is the name white? What is white in that noise? Or what is white color here? Why am I saying T here? I'm very sorry about that. It is, of course, the frequency. Why is the name of this thing white? What could be the reason? Of course, you have to think of the color itself. What is unique about white color? Beg your pardon? Yes, exactly. It is the color of sunlight, white light, in other words, which is a combination of all the wavelengths of the light, including red, blue, green, orange, yellow, whatever, purple. All the colors are equally included in the white color. And that means wavelengths are, by the way, 1 over frequencies. So if you just take the reciprocal of omega and say 1 over omega, and if you just plot it on the axis of lambda, the wavelength, which is 1 over omega, it would again be 1s. And therefore, if a color contains all the colors, the combination color is a white color. That's why they call it white. And if the spectrum of the signal is as flat as this one, they call it a white noise sort of thing. So impulse is an example by itself for a white noise, interestingly. There are further concepts that that you don't need to know for the time being, because They are telecommunication concepts. Of course, it's not the Fourier transform of the signal they look at for noise signals, because noise signals are not deterministic. So for non-deterministic or random signals, you don't have Fourier transform. You must first find the so-called autocorrelation of the signal, and then take the Fourier transform of the autocorrelation. That would be white. So that's a different story. But from the light back to the concept, if you use a prism, you remember the physics experiment. If you pass a white light into a prism shape, at the other side of the prism you see separate colors. Okay? You remember that physics experiment? From red to purple, all the colors will be there. So that prism corresponds to some sort of a Fourier transformer, or even a bandpass filter. It's like the cascaded arrays of bandpass filters depicting this frequency range, this frequency range, this frequency range, etc., and then separating them. Therefore, it is some sort of a Fourier transform. I'm not, again, going into the details of that, but there is a strong relation between optics and Fourier theory for the curious. So it's not only the electricity or signal processing or signal sense systems or computers that is related with Fourier. The Fourier transforms or frequency separation is a very natural phenomenon, and it can even be found in the nature in the form of optics. Optics is related with that. The lenses, etc., they all take the Fourier transforms of two-dimensional signals, which are images. So they are interesting things, and I somehow recommend the curious students to take a look at them. What's the relation between a Fourier and a lens? What's the relation between a Fourier transform and a prism? What's going on in optics? So those are all for the curious students, but this one is for all of you. So if you have an impulse, x of t is equal to delta t, the Fourier transform of that is equal to 1, which is an all-pass Fourier transform, totally constant. Now, let's start with another example, and in this example we will demonstrate that the shape of the Fourier transform in Fourier domain or frequency domain on the omega axis, and the shape of the time domain signal. We have two representations of the same signal, you see. We have x of t on t axis, and we have x of j omega on omega axis. What I'm telling you is that the narrowness or the squeezedness or stretched versions are inversely proportional in both axes. So if a signal becomes very, very narrow in time domain, then it means its Fourier transform is getting very, very wide. That's why, in fact, impulse, which is the narrowest signal that you can have, it is with 0, will correspond to the widest signal in the Fourier transform, which is all ones, completely flat. But somewhere in between, the proportion is inverse. Okay, they are inversely proportional to each other. So let's see it in an example of a rectangular shape time domain signal and its corresponding Fourier transform. So the time domain signal, the rectangular time domain signal, is a rectangular box which is 1 between minus t1 and capital T1 and 0 else. So this is a signal, as you see, from minus t1 to t1 on the t-axis, and this is x of t, and the peak is 1. So what is the Fourier transform of this thing? Let's start by finding it. And it is so famous that probably long after finishing this course, you may remember the name. We have already started using that expression already. The shape of the signal output is sinc shape. Sine of t over t. Sine of t is an oscillation, 1 over t is a decay, so sine of t over t will be a decaying oscillation. from the peak, and then there will be a damping, and it's a decaying oscillation thing. And the Fourier transform for this one is from minus infinity to infinity x of t times e to the minus j omega t dt. That's the formula. But x of t is 1 only from minus t1 to t1. So it's not from minus infinity to infinity, the integral limits. It is only from minus t1 to t1. If you overshoot in both directions, then it will be x of t will be 0, so it will not contribute to the integral. And in between this range, x of t is 1. E to the minus j omega t dt. Now, you can clearly develop the integral using calculus. And then, since it's in the exponent form, you just have to say 1 over the exponent times the exponent itself from t1 to minus t1. And but I'm not going to do that because it's just cumbersome operation. I'm just going to write you the formula. When you just reduce it in a more compact form, this is the simplified form of that expression, as simplified as possible. And now this is a sink shape. And this sink shape is a famous one. It's a sink shape on the omega axis, of course. This is a function of omega, we find. In time domain, sink is sine t over t. In frequency domain, sink of omega is sine omega over omega. In fact, the true definition of sink of x is equal to sine pi x divided by pi x. Okay, this is the correct form of sink, the standard form of sink. And in terms of sink, we are able to write it, or we can express it without pi's or anything. But now let's forget about the name. How does it look like? And where does it make a zero crossing, etc.? That is the point that you have to be careful about. Let's be a little bit focused on what happens at omega is equal to 0. Sine omega, 2 times sine omega t1 over omega. What is the value of this at omega is equal to 0? Really? The denominator is 0, but so is the numerator. The numerator is also 0. Because sine 0 is 0, and 0 is also 0. So it's a 0 over 0 thing. And you have to apply the Hospital's rule. And you will see that when you take the derivative of sine omega t1 with respect to omega, t1 will go out, and the cosine will come into the picture. And the denominator will be, the derivative will be 1. So t1 times cosine 0 is t1 over 1. So the whole thing converges to t1 as omega goes to 0. And since it is multiplied by 2, it is 2t1 at omega is equal to 2. Omega is equal to 0. So this is the situation. The peak point that you have is 2t1 at omega is equal to 0. And if you just plot it using, say, MATLAB or any kind of a plotting tool that you may have in your computers, just avoid omega is equal to 0 point, and at that point it is equal to 2t1. You will see that it's a decaying envelope shape. So let's draw the envelope, and it makes oscillations like this. Now it's a nice exercise to try to find this, and I have to give it to you as a homework, because otherwise I'm not going to collect it, then it's not a homework, it's just an exercise. But without doing this exercise, you will not be able to properly label where it makes the zero crossings. Okay, you have to just first work on it a little bit. So whenever you come up with a more complicated form of sync, you will find the zero crossings. And when I say in the exam, when I say plot the Fourier transform, it means that I'm asking for some labels on the plot. For example, what is this peak value here? And where are these zero crossings? What are these zero crossings? Let me give you a hint about this. The zero crossings, at 0 there is no zero crossing, but other than that, wherever this zero crossing is, say that it's omega is equal to x, the next one is at 2x, and this one is at 3x, 4x, 5x. So the zero crossings are equally separated, and the magnitudes are decreasing. This is the sync shape, but what is this x? For 2 sine omega t1 over omega sigma. Is it? It should depend on t1. As a matter of fact, the whole idea of this example is to show you that it is inversely proportional to t1. That is, if this top shape becomes wider and wider, that means t1 is larger and larger, then this sync shape will be more and more squeezed, showing more and more oscillations. Therefore, this x is inversely proportional to t1, of course. As a matter of fact, you can find it. When is a sine making a 0 at the angle to be equal to pi, isn't it? So when is it equal to pi? At omega is equal to pi over t1. It's not pi, it's pi over t1. So if t1 is increasing, if the original rectangular time domain signal is wider, then this sync shape is even more squeezed. And conversely, if t1 is smaller and smaller, this shape, this sync shape, will be wider and wider. The oscillations will be a large number. By the way, since there is also a t1 at the peak, if that t1 becomes smaller and smaller, the magnitude is also becoming smaller and smaller, because the top shape, if you decrease t1 to 0, it means you are just annihilating the signal. The signal stops existing. It will be a smaller energy, smaller energy, smaller energy, smaller energy, and then at t1 is equal to 0, there will be no energy, and the signal will be completely 0, whose Fourier transform will again be completely 0, because this peak will go down to 0. So, in terms of shapes, what we can say is something like this. As an illustration, without any proper labeling, if you have a wide signal, then the corresponding Fourier transform will be a sync that is quickly oscillating with high frequencies. And if it is a narrower rectangle, then the Fourier transform will be with wider oscillations. So the Fourier transform will become wider if the signal is narrower, and if you even make it narrower than the previous case, then the Fourier transform will of course be even with wider oscillations like this one. So this is the general phenomenon. This kind of a phenomenon exists for every shape. They are always inversely proportional. So whenever you find the Fourier transform of something that I give you, and its Fourier transform is there, if the question just modifies how wide it is, shrinked or stretched like that, you have to just inversely proportion the Fourier transform shapes. If you shrink the shape, then you have to stretch the Fourier transform. They are inversely proportional. Why are they inversely proportional? It's quite obvious, I guess, because the period, which is in terms of the time, as we know, is inversely proportional to the frequency. Frequency and time are inversely proportional concepts to each other. Okay? So that's what we have to be careful about. And one other hint, which will be provided to you in the next hours, in the forthcoming hours, as properties, because we are going to list down properties, as we all know. That's what we always do. We list properties of Fourier series, we list properties of Fourier transforms and things like that. We will do that, but for the time being, let me give you another hint. The Fourier transform and inverse Fourier transform shapes are interchangeable. So what I mean is this: if you have this time signal and its Fourier transform is this, then you have to expect something like this. If you have this shape as a time signal, then its Fourier transform will be like this. The inverse and forward Fourier transforms come up with the same shapes. The Fourier transform of a rectangular time signal is a sinc. The Fourier transform of a sinc-shaped time signal is a rectangular Fourier transform. They are dual of each other. We will come back to that later. Or we can start feeling about that with just one example. Like this: x of j omega is a rectangular shape, one for frequencies less than capital omega and 0 else. So it is a low-pass, ideal low-pass filter with a bandwidth of omega, w, sorry, from minus w to w, a rectangular low-pass signal or a filter. What is the time domain counterpart of that? So what is the impulse response of an ideal low-pass filter? It's an alternative question of that. Because this is an ideal low-pass filter. So what is the impulse response? The time domain counterpart. And for this one, we need to this time use the inverse Fourier transform. And the inverse Fourier transform is, you may or may not remember, but if you check out the formulas that we provided, from minus, with a 1 over 2 pi, from minus infinity to infinity, x of j omega, e to the j omega t d omega. This was the inverse Fourier transform. And x of j omega is 1 between minus w and plus w. So the integral limits are from minus w to plus w, because when we overshoot that, x of j omega will be 0. There will be nothing here. And within this range, x of j omega is 1 times e to the j omega t d omega. As you see, this integral is very similar to the previous integral. What was the previous integral that I didn't solve? It was here, from minus t1 to t1, e to the minus j omega t dt, which is sinc. And this time, it is from minus w to w, 1 times e to the j omega t d omega. And of course, it's not a big surprise to come up with a sinc shape again. Like this. On the time axis, t-axis, it is sine t over t within some scales. You have to just check what happens at t is equal to 0, what is the value at t is equal to 0, first, step number 1. When I say plot it, you have to tell me what is the peak of that sinc, what's the peak value, and where are the zero crossings. So what is the peak value first? At t is equal to 0, what's the value of this? No. Okay, the sign itself, when you take the derivative, the inside term goes out there, and it becomes a cosine. So it really behaves like without the sign. Just forget about this. Wt over pi t. What's the value of that at t is equal to 0? T is cancelled. It's w over pi. Simple. So the shape is the peak is w over pi. And where are the zero crossings? The zero crossings are determined by the value of sine wt to become pi. So at t is equal to pi over w. It's the first zero crossing. The others are just integer multiples of that. 2 pi over w, 3 pi over w, 4 pi over w, etc. And minus pi over w, minus 2 pi over w. It goes on like this. And it's again a sinc shape on the time axis. This is equal to x of t. We are all drawing this. And the inverse shrinking versus stretching phenomena also exists in this kind of an inverse Fourier transform as well. As you see, as W increases, the low-pass filter's bandwidth will become wider and wider, and the corresponding time domain signal, which is sinc, will be narrower and narrower, sharper and sharper. Okay? They are inversely proportional to each other. Okay. Another example. Now this example in my notes is an example about what to do for periodic signals. Because for periodic signals we haven't defined the Fourier transform yet. What do we have for periodic signals? We have the Fourier series. You remember that? The previous chapter. But a periodic signal is a subclass of a more general class of signals. It's not just another arbitrary signal. It's just a periodic one. So how can we describe the Fourier transform with respect to that? In other words, if you have x of t whose Fourier series coefficients are AKs with a fundamental frequency of omega 0, of course, you have to define the fundamental frequency and the Fourier series coefficients, then how can we construct the Fourier transform from that? We just have to insert impulses at the positions of the Fourier series coefficients. We were already doing that when we were filtering, trying to filter the periodic signals. You remember that? We were drawing on the frequency axis the Fourier series coefficients, 2 of them, 3 of them, or infinitely many of them. And then we were just putting impulses over there. Now, let's find the proper way of inserting the real impulses there. What we need to do is we have to define the Fourier transform of x of t, which is x of j omega, and define it in terms of AKs like this. It's a infinite summation of 2 pi scale, infinite summation of because AKs can be from k is equal to minus infinity to plus infinity. For all AKs, an impulse is inserted at the proper frequency of that AK. What's the frequency of that AK? K times omega 0. That is the frequency. So we insert an impulse at the corresponding frequency. The corresponding frequency is k times omega 0. For example, if it is A0, the DC, what we do is we insert an impulse at omega is equal to 0. because k times omega 0 will be 0. Delta omega is an impulse at omega is equal to 0, and we just scale it with ak. Let me give you an illustration. Suppose that a0 is 1, a1 is equal to a minus 1 is equal to 3, and a2 is equal to a minus 2 is equal to 4. So it's a combination of cosines, you see. We have two cosines at a1 and a minus 1, and a single cosine with two Fourier series coefficients, and another cosine at a2 and a minus 2, plus a dc, plus 1. Can you think of the time domain signal corresponding to this, by the way? Do you want me to write it? It is 1 plus 6 cosine, and we have to define, sorry about that, we have to define omega 0 is equal to something. Just give me a frequency, 10 pi. So this one is 1 plus 6 cosine 10 pi t plus 8 cosine 20 pi t. So this is the time domain signal we have, and the top things are the corresponding Fourier series coefficients. Do you agree with that? 6 cosine 10 pi t, what are the Fourier series coefficients? 1 over 2 times 6 and 1 over 2 times 6, which are 3 and 3, that they are given there. Okay, so how do we draw this on the frequency axis? What is the corresponding Fourier transform, in other words? What is x of j omega? And I will give the answer by just drawing it. It's like this. X of j omega is equal to 2 pi times ak. The impulse values, impulse magnitudes are 2 pi times ak's. For example, 2 pi times a0 at the top. What's the value? Therefore, it is 2 pi times an impulse. Where is that impulse? At k times omega 0 and k is 0. So it's at omega is equal to 0. So this is our first impulse with the magnitude of 2 pi. Where's the next impulse? The next impulse is at the corresponding frequency, which is 10 pi. Let's assume it is here. 10 pi. And I have to insert an impulse here. What is the magnitude of that impulse? It is 2 pi times a1, and that is 3. So it is 6 pi, much larger impulse. Beg your pardon? Okay, here it is. This is the formula. It is 2 pi times ak. That is the magnitude. And ak is a0 is equal to 1. So 2 pi times 1 is 2 pi. That is the magnitude. Where is it? At delta omega, because k is equal to 0 would make delta omega minus 0, which is delta omega, which is the 0 frequency. It's in the center. It is this impulse. And the magnitude is 2 pi times 1. Here, the magnitude is 2 pi times 3, which is 6 pi. And where is it? It is at the corresponding frequency. And the corresponding frequency for A1 is equal to 10 pi. And by the way, the frequency for A minus 1 is minus 10 pi, so we have to draw another impulse of 6 pi at minus 10 pi as well. Another impulse here. And then we need 2 more impulses. Where are they? At 20 pi and at minus 20 pi. What are these? What are the magnitudes of them? It's what? 2 pi times 4. No. It's 2 pi times a2. A2 is 4. It's not 2 pi times 8. It's 2 pi times 4. Because in the earlier expansion of the cosine, you have 1 over 2. Okay, don't forget that. So 2 pi times 4 is 8 pi. And this one is 8 pi as well, at minus 20 pi. So this shape is the Fourier transform, x of j omega, the proper way of answering the question. Or I may ask you to write it in terms of an analytical expression, not plot, but write down the expression. Then you have to tell me this. X of j omega is equal to 2 pi delta omega plus 6 pi in parentheses delta omega minus 10 pi plus delta omega plus 10 pi, which are two impulses at 10 pi, the first one, and minus 10 pi with the second one. They are all scaled by 6 pi plus 8 pi in parentheses delta omega minus 20 pi plus delta omega plus 20 pi. And then if I tell you to write down the expression, what I'm expecting from you is this. Okay, is that clear? This is the Fourier transform. So what I'm telling you in short with this example is the follows. If I ask you the Fourier transform of a periodic signal, don't use the formula for the Fourier transform, which is an integral. Don't use it. First, just find the Fourier series coefficients. Use the formulas and your prior knowledge about Fourier series. Okay? Find the Fourier series coefficients, AKs. And then scale those AKs by 2 pi's and insert impulses over there. The constructed thing, this shape, this shape that we have there, is the Fourier transform. That's the method to do it for periodic signals. Okay? Now, finally, let's give a very simpler case of this one. This was more complicated. X of t is equal to e to the j omega 0 t for some omega 0. This is a periodic signal, isn't it? Because it's a complex sinusoid. And I'm asking you, what's the Fourier transform? What's the Fourier transform? For this, you need to find the Fourier series coefficients of this signal. What are the Fourier series coefficients? When something is too simple, it's sometimes confusing. What are the Fourier series of this? The question in itself is a little bit misleading when I say what are the Fourier series coefficients, because this is only one harmonic. It has only one Fourier series coefficient, and it's itself, and the Fourier series coefficient is 1 times the complex expansion. So what's the Fourier series coefficient? It's 1. A1 is 1. And what is the frequency? It's omega 0. So what are we going to do? We are going to draw it on the frequency axis, find omega 0, let's say it is here, and we are going to insert an impulse at the position of the Fourier series coefficient, which is 2 pi times this, which is 2 pi, of course. Is that it? That's it. Yeah. So this is the Fourier transform, as simple as that. A single impulse. Or if you want to just write down the expression, then you have to say that x of j omega is equal to 2 pi delta omega minus omega 0. Simple. When things are too simple, it may be confusing, but as you see, it's as simple as this one. Of course, if the signal is more complicated, and if it has a lot of Fourier series coefficients, then you just have to put impulses at those a lot of Fourier series coefficients, multiplying all AKs by 2 pi. You have to draw it like this, or like the top tip. Okay. So that's a methodology to evaluate the Fourier transform for periodic signals. We will go back to the non-periodic cases. We will see other examples, but now we can give a 15 minutes break. After the break, we will continue.